About symmetry and tessellations. So symmetry you've heard about before. A figure has a line of symmetry if the figure can be mapped onto itself by a line of reflection. Now, mapped onto itself kind of implies that if you were to fold it on that line of symmetry, it would lie on top of itself. Okay. Or if we're drawing it out, what it means is that if we draw from any point on the curve to the thing which we're checking for symmetry with respect to, so in this case, this vertical line, and we continue that same distance on that same line, we should lie on top of another point on the curve. So from any point to the line we're checking for symmetry with respect to, continue that same distance on that same line, and we should hit a point on the curve. And so this works for any curve on the shape. Same distance on that same line, we hit another point on the curve. And so that's a way you can visually check for that mirror image, checking for that line of symmetry. Now, point symmetry is when a figure is mapped onto itself by rotating the figure 180 degrees about a center point. This means, now they say this means that it looks the same upside down. More than upside down, it's really rotated 180 degrees. So if we did a 180 degree rotation, that it would look the same. Okay. Now, when we're checking for point symmetry, just like when we're checking for line symmetry, if the point that we're rotating about is here at the center, we can do that same visual check, meaning we can draw a line from any point on the shape to that thing we're checking for symmetry with respect to, so this time a point, continue that same distance on that same line, and we should hit another point on the curve. So from any point to the thing we're checking for symmetry with respect to, same distance on that same line, we'll hit another point on the curve. So there to the point of symmetry, same distance on the same line, we hit another point on the curve. So you can, I think that's awesome that you can use that same check of drawing a line from a point to the thing you're checking with for symmetry with respect to, same distance on that same line, whether you're talking about line symmetry or point symmetry. And we'll do this a lot in pre-cal as well. That's kind of exciting that you guys are already doing important stuff that you'll continue further with in pre-cal. Okay, so examples in nature. Mostly we can visually recognize symmetry. We see that a butterfly is symmetric, that the two wings would map onto each other across that line of symmetry. We can even see it in letters. A vertical line would divide A into equal parts. A horizontal line would divide B into two equal parts. X could be divided either horizontally or vertically. Even some words have symmetry. The word mom, if you divided it in the center, it would map onto itself. The word he, now this is kind of cool. A horizontal line, if you folded it across that line, it would map onto itself. Polygons can also have symmetry. So here, this square, if we folded it on the diagonal, it would lie on top of itself. If we folded it on a vertical line through the center, it would lie on top of itself. If we did it through a horizontal line, it would map on top of itself. And of course, the other diagonal as well. So sometimes shapes have multiple lines of symmetry. So take a look at this equilateral triangle. So a vertical line through one vertex, which means a vertical line, because it's equilateral, through each of the vertices would do it. So from this vertex, okay, so this has 3 lines of symmetry on an equilateral triangle. What about a rectangle? What do you see? Well, we could divide it in half, and it would map onto itself with the vertical line, or we can divide it in half horizontally, and it would also map onto itself. So lots of examples of symmetry, and we just have to start to look for it. We may not be used to looking for it on the diagonal, but we can certainly do that. Okay, so this says list all the capital letters that have vertical line symmetry. So we already said the letter A does. Let's try that again. So that would be the letter A. The letter B won't, the letter C won't, D won't, E won't, F won't, G won't, H will. H, we can draw a line there, and it would have vertical line symmetry. The letter I would, if we drew a skinny line right in the middle of it. Maybe yours is more in the middle of it. So the letter I would, even if we did it like a traditional capital I, it would have that vertical line symmetry, so I'll do it like that. J, K, L won't, M will. We can divide it in there. So I'm just literally going down the list, looking to see if I can draw a line and it will fold over on itself or map onto itself. O will. Oh, no, S won't. Okay, and then T will. U will. You will. V will. W will, the U will if it's made like that, not if it's made like other. X will, Y will. You can split that right down the middle. Okay, but Z will not. Okay, then let's go ahead and try the next ask for which capital letters have horizontal line symmetry. So now this time we're looking for a horizontal line that will divide it in half. Now I must say on the B's, it depends on how you make your B. Some people make it with the top part a little bit smaller, but if you make the top and the bottom the same side, then it would have horizontal symmetry, as will the letter C, as will the letter D. It would fold over on itself or map onto itself. Letter E would do it. Not F, not G. Ooh, H will again. Okay, and I will if we fold it that way. Okay, so even if we do the more traditional capital I, no, no, no. So the K depends on how you make your K. So if you make your K like this, it won't. But if you make your K like that, then it would. So I'm going to put that one there because if we made it like that, it would. Not like this one. Oh, but then look, then I didn't draw it symmetrical. So it would depend on how you make your K. So I would say that kind of a K would. O will. X will. And it looks like that's about it. So it says list all the capital letters that have both vertical and horizontal. So let's see, we had B, C, D, E, H looks like the first one, then I, then O, then X. Those were the four that had both horizontal and vertical symmetry. Now it says list all the capital letters that have point symmetry. So what we're looking for here is if it has a central point that we can rotate 180 degrees about and it would lie on top of itself. So let's go see if we can spot those points. So if we rotated H, the point H, around a central point, if I rotated it 180 degrees, you wouldn't know I had rotated it because it would still look the same. And that's what we're saying. So if we spun it 180 degrees, it would still look like capital H. Let's see. I, if you spun it 180 degrees, it would still look the same, even if we drew it with a capital I and O. And now this is interesting. Look, if I did a 180 degree rotation, then this part here would be at the top, but it would still look like capital N. And so capital N has that 180 degree rotation. No surprise that O does. We can rotate O and it'll still look the same. Now, here's where I was thinking about S earlier. If we spin S 180 degrees, it will still look like capital S. So that's kind of cool. Same thing with X. If we rotate it 180 degrees, it'll still look like X. And Z, if I rotate that 180 degrees, this part that was down here is now at top, but it still looks like capital Z. You can't tell the difference because it still looks the same. I guess I'm used to putting the line through the middle of it. I shouldn't do that if we're doing the regular symmetry. Okay. Will it look the same when it's rotated 180 degrees or a straight line rotation? That's what we're looking for. If you rotate it 180 degrees around that central point, will it still look the same? Okay. How many lines of symmetry does each figure have? So the starfish, kind of similar to the triangle when we looked at it, we can draw a line of symmetry through each of its different vertices. So let's draw those in. So we could have that one. We could have that one. We could have that one. And as we move around, we could have this one. We could have this one. Okay, now if we want to count those, my strategy for counting them is to start here at the top and count your way around until you get to that same red line that we start with at the top. When we hit at the bottom, we will have seen all of the different lines. So we have the red one, the blue 2, the orange 3, the purple 4, the green 5, and we're done counting because we're back to red, which we've already counted. So this had 5 lines of symmetry. Okay, so here with this flower, now this is interesting. It has some of the obvious symmetry. So we have that one, the horizontal and vertical that you might think of, but we also have diagonal symmetry, and maybe you thought of those too. But is that all? Be careful. So just like we could draw a line of symmetry through the points on the starfish, if we draw a line of symmetry through that petal, it'll still fold on top of itself. So we'd have that one, we could have this one, we could have this one, and it looks like we could get one more in there. Looks like we could do this one. And again, to count those, I'm going to start at the top, vertical, and when I get to the bottom, I know that I will have counted them all. So I have orange 1, pink 2, light blue 3, light pink 4, red 5, green 6, purple 7, maroon 8. And when I get back to the orange, I know that I've counted them all. I'm not going to count the orange twice because I already counted it at the top. So that'll be 8 lines of symmetry. Now for an easier figure, we kind of been counting a bunch. This one has a horizontal line of symmetry and it has a vertical line of symmetry. So just 2. The hexagon kind of has a lot again. Again, we could fold it vertically. We could fold it horizontally. We could do it through each of its vertices because this is a regular one. Boy, those are not good lines of symmetry. Let's see if I can draw it a little bit better. 3, 4. What about, I'm trying to think. Yes, if we lined that up, it would, just like if that was on the top and that was on the top. This time I did them all in the same color, but I'm still going to count starting at the top, and when I get to the bottom, I'll know I'm done. So I have 1, 2, 3, 4, 5, 6, and I'm done. So it has 6 lines of symmetry, which is kind of cool because it was a hexagon and it has 6 lines of symmetry. If you think about it, each one just comes through the top and sides. Now, what about this next thing? Well, it is possible to have no lines of symmetry. This has none. I can even turn that 0 into a none. Not all such shapes are symmetrical. This shape is not symmetrical, so don't forget that that's always an option. Okay, so do these have point symmetry? The next shapes, do they have point symmetry? So remember, we're checking, is there a central point that we can rotate around that if we rotated it 180 degrees about that point, it would lie on top of itself. It would look the same. Well, sometimes this is the hardest symmetry to visually see, so I recommend doing our little test where we draw a line from any point on the shape through the point, continue that same distance on that same line. If we lie on another point on the shape, then it is symmetrical about it. But this has to be true for every point on the shape. So if you go from any point to the thing we're checking for symmetry with respect to, this time a point, continue that same distance on that same line. Oh, that was not the same line. Let me get it kind of lined up better. Okay, so from any point through the point, same distance on the same line, and you should hit another point on the curve. And you can see here, no matter what point I pick, if I go through that point and continue the same distance on the curve, I do hit another point on it. Can you see visually how if I rotated this 180 degrees, it would look the same? I wouldn't be able to tell that it was different. So yes, this does. Now here, if I grab this point at the top and continue and draw a line to the point in the center, if I continue that same distance on the same line, I do not hit a point on the curve. This one does not have point symmetry. Let's check this next one. Now on this one, I think it's interesting. So if we grab a point at the diagonal through the point, same distance, same line, we hit a point straight above through the point of symmetry, same distance on same line we do. And it's got to be true for every point. So try some points from different locations. And no matter where I pick my point from, when I continue that same distance on that same line, I do hit another point on the curve. So yes, this one does have point symmetry. If you rotated it 180 degrees, it would still look like a rectangle oriented horizontally. Let's try this last one. Draw a line from any point to that curve, continue that same distance on that same line. Wah, wah. I do not hit a point on the curve. So that trapezoid, if I rotated it at 180 degrees, then it would look like the bottom was wider and the top was narrower. It would not look the same when rotated 180 degrees. And that's what point symmetry means, is that if you rotate it 180 degrees around a central point, it will look the same. Okay, so let's try this with words now. Now we won't be drawing our line here. We want to visually work on seeing this 180 degree rotation that we're testing for. If we rotate it 180 degrees around the central point, will it look the same? Okay, so if I put my central point was in the middle of the word mom, if I rotate it 180 degrees, it will look like wow. it'll look like wow. If I turn it 180 degrees, it'll look like wow. So that does not have point symmetry. But the word mo, if I rotate it 180 degrees around a central point, it will still look like mo. It does. This W will become the upside down M. This M will become the upside down W. And so that one does have point symmetry. Okay. Now let's take a look at the word swims. So if that central point, it rotates, the S still looks like S when it rotates. The W now looks like the M now looks like the W, and the I still looks like itself. Swims does have point symmetry. That central point there, so it does. The word math, not a chance. That H, when you flip it around, will be where the M is. Oh, what do we think about the word noon? What do you think? What do you think? You betcha. Now this time the point would be in between the words, but it's in the center of the word there. And if we rotated it 180 degrees, it would still look like the word noon. So that's kind of awesome to see that. That may not be something we've looked for or thought about before. Okay, so which of these cards, if any, shows point symmetry? Now, I'm sure a lot of you have played cards before, and you know that there's not a right side up of the card. As far as if the 9 is up, it looks like a 9, or if you had your card the other way, it would still look like a 9. And we've got 4 hearts facing one way and 4 facing the other way, so those will look the same when we rotate it 180 degrees. But what about this heart in the middle? Right now, this heart looks like it's right side up. If I rotate it 180 degrees, then that heart will no longer look like it's right side up. It'll look like the point is at the top instead of the heart. So this does not. You can test again by drawing from the heart to the center point, same distance on the same line. You do not hit a point on the heart. So this one does not. But if we're looking at a diamond, the diamond shape, whether it's right side up or wrong or upside down, we can't tell. If we look for that central point of rotation and draw a line from a tip to the point, same distance on that same line, we hit another tip, side through that point, same distance, we hit another point. And so this one actually does have point symmetry. It does have point symmetry because on the diamond, it looks the same when you rotate it that 180 degrees. Okay. Now, for this last symmetry shape, I think, it says circle all the lines of symmetry for the following square. So we've got to remember from Algebra 1 what y equals and x equals lines look like. Remember our HOIVUX acronym that helped you remember. Horizontal lines have 0 slope. They are y equals equations. It's HOIVUX. Vertical lines have undefined slope. They're x equals equations. So when it says x equals 2, that's a vertical line at x equals 2. If I fold my shape across that line, will it map onto itself? Meaning if I draw a line from any point to that line, go that same distance on that same line, do I hit another point on the curve? No, I do not. You can visually see that that is not going to divide the shape equally in half, so that one is not. I'm saving that first equation for later. Let's do some of the easier lines first. The next x equals equation is x equals 0. So if I draw on the line x equals 0, that's that vertical line. Okay, maybe yours looks better than mine. Okay, and so, and most of you can visually see, you betcha, that is a line of symmetry. If you're not sure, do our test from any point to the line, same distance on that same line, and I'll hit a point on the curve. And it's the shortest distance to that line of symmetry. So we would go straight to it from any point to the line, same distance on the same line, we hit a point. And so you can see it does have that symmetry. Okay, let's check the next equations. Now, y equals equations are horizontal lines. So let's check our first y equals equation. So they said y equals -1. If I draw in the vertical line at y equals -1, I can see right away that is not dividing it in half. You can do the drawing test if you need to, but I don't need to. I can tell that one doesn't work. Okay, what about y equals 0? The horizontal line at y equals 0. Visually, I can tell, you betcha, that will fold over on top of itself. Now we get to do the harder lines to see, and that's the line y equals x. They're not really harder to see, but we just have to graph them correctly. So y equals x has a slope of 1 and a y-intercept of 0. That is the line that goes through 0 with a slope of 1. And so that is the linear parent function. So there we have it graphed right there. And once I have it graphed, I'm like, oh yeah, if I fold across that, it will be symmetric about it. If you weren't sure, you could draw a line from any point to that line, continue that same distance on that same line, and you would hit another point from any point to that line, same distance on the same line, we'd hit it. And that would be true for any point that I picked. If I went that same distance on that same line, I would hit another point on the curve because it is symmetric about that line. Okay, similarly, if we look at the line y equals negative x, it also has a y-intercept of 0 and a slope of -1 this time. So now it's a decreasing slope. So that's going to have a y-intercept of 0, slope's -1. So that's that line. It also divides it in half just on the other diagonal. So those 4 would be lines of symmetry for this shape, but not the other 2. Okay, so we're doing symmetry and tessellations. Now let's talk about tessellations. A tessellation is a pattern of a shape that is repeated over and over so that the shapes have no gaps and that they never end. Each vertex must look the same and all the angles must add up to 360 at any given point. So a regular tessellation would be a single shape that fills the plane. This kind of looks like a bee's honeycomb, and it would completely fill the plane. Now, I mean, like, because you can see where we could just keep going and draw. We have to stop at some point just for drawing's sake, but you could see where you could continue that pattern. Okay, maybe if you're a better drawer than me, but that it would continue and keep going forever. Semi-regular tessellations mean they have the same pattern, but it's not just one shape over and over. So these octagons have those squares in the middle of them, but together it completes the pattern and could continue to fully fill the plane. Now remember, it said that at any given point, okay, where the vertices meet, they have to form 360 degrees. They have to fully cover all the open space. So if we add these 3 angles, 1, 2, and 3 together, they'll sum to 360 because they'll completely fill all of that space. Even on this one with the semi-regular tessellation, if you look at those 3 angles, the angles aren't all the same this time. These 2 angles would be the same. That third angle would be much larger, but altogether they would add up to 360 degrees so that they fully fill all the space. Okay, and that's how you can check to see if something will tessellate. When you put the angles together, will it fully fill that 360 degrees? Okay, so our next question is, which of these polygons will tessellate? Which of them will tessellate? So now it says regular polygons, meaning that they have the same size sides and the same size angles. So a regular triangle is an equilateral triangle. All 3 sides are the same and all 3 angles we know are 60 degrees. And so the way to check to see if a triangle can tessellate a plane is to take 360 and see if those 60-degree angles at each vertex, see if they can divide evenly into it. Could they fill that fully? And 360 divided by 60 is 6. It would take 6 triangles. But because it's an even number, okay, let me write this in another place. Because that equals 6, therefore it will tessellate. If it divides evenly into it, it will tessellate. And so rather than writing out will tessellate, because we're short on space here, I'm going to put yes. Which of these will tessellate? This one will. Okay, so what is a regular quadrilateral? Well, quadrilaterals have 4 sides. And if all 4 sides are congruent and all 4 angles are congruent, we know that those are 90-degree angles because a quadrilateral sums to 360. So those are each 90-degree angles, okay? And so if we take the 360 that their vertices have to meet and fill, 360 divided by 90 equals 4. It equals a whole number. Therefore, yes, it will tessellate. Okay, so far so good. What about a pentagon? A pentagon has 5 sides. Okay, now I'm not going to keep drawing because I'm not that good of a drawer of regular shapes, and it's easier to do this mathematically anyway. What is the angle sum of a regular pentagon? Well, that's 180 times 5 minus 2 divided by 5. And so each angle of a regular pentagon is 108 degrees. We learned that in our first lesson of the unit, how to get the angle measure of one angle of a regular pentagon. And then I want to see, will 360 divide evenly by 108? Will 108 divide evenly into 360? And of course it doesn't. That ends up being 3.3 repeating. So it does not divide evenly. And so since it doesn't divide evenly, it can't fit together to fully make that 360 nice tight connection at a single point. So therefore no, because it wasn't a whole number, it will not tessellate. Okay, what about a hexagon? What's the measure of a single angle of a regular hexagon? Well, let's do our little formula, 180. The hexagon has 6 sides. So times 6 minus 2 divided by n, so divided by 6. Each angle of a hexagon ends up being 120 degrees. Now, can those angles of a hexagon, those 120 degree angles, can they fit together tightly to form a full 360? Let's check. Will 360 divide evenly by 120? You betcha it will. It divides in 3 times. Therefore, yes, it will tessellate. Okay, so what we're checking, we have to find what one angle would be of a regular polygon, and then see if that one angle will divide evenly into 360. So what about a heptagon? So that's 180. Heptagon means n equals 7. Working on that vocabulary. 180 times 7 minus 2 divided by 7. This is just our formula for finding a single angle of a regular polygon. So I get that that's 128.571 approximately. Now, if it doesn't even make a whole number itself, it can't divide evenly into 360. And so this is not going to be able to divide evenly into 360. Okay. And if we start thinking about what numbers do divide evenly into 360, we've actually already hit them all. 60 goes in 6 times, 90 goes in 4 times, 120 goes in 3 times. And so the next number that would divide evenly would be 2 times 180, but 180 is a straight line, so it's not an angle. So it's going to turn out that none of these other sizes work, because there are no more numbers that divide evenly into 360 that are our angles of our polygons, but you could follow the same process to check. You could find the individual angle of it, so let's do one more of those to practice. So if we did 180 times 8 minus 2 divided by 8, we would get that the angles of an octagon are 135 degrees each if it's a regular octagon. If I take 360 and divide it by 135, I get that it's approximately 2.6 repeating. And again, it makes a decimal, therefore it does not tessellate. Okay, we need it to divide evenly perfectly in. So triangles will tessellate. Quadrilaterals, regular quadrilaterals, which are really squares, will tessellate. Hexagons will tessellate. Okay, and so like you can draw and see that triangles will tessellate, that you could draw them and that they will fill all of the space around a single point. Okay, and while you're at it, those triangles make a hexagon, which we also said hexagons tessellate. So if you were to go, those hexagons could also tessellate. And so you can see around a single point they could meet to tessellate like that. Obviously, quadrilaterals can when they're irregular, when they're squares. We lay tile and it's just square next to square next to square next to square, right? Like that's how we lay tiles, okay? So that's kind of interesting. Okay, and that's how you could do it. You could check for any shapes, find out what the regular angle is, and see if it divides evenly into 360 to see if it'll tessellate. Okay, and then our last problem of the day. So if we can see this tessellation, now these aren't from polygons, these are shapes, and Escher is an artist famous for his tessellations that he came up with. So this is fish drawn just so that they will make a regular polygon. So that they will make a tessellation. They're not regular polygons, but they will still make a tessellation. Now, the thing of it is these shapes are the exact same size and their angles are the same measure in each of the different fish. So it's not that all of its angles are the same, but they're the same in each of the fish. So here it says some of the angle measures are given for one fish. What is the value of x? So take a look here. I know this figure is kind of small. If we look at this straight line here, that is a straight line. We know straight lines are 180 degrees. So they would like to know what this angle here is. They'd like to know what x is. Okay, they've labeled that as x. Draw it a little bit bigger. So what we need to do is we need to find out what this angle of the fish is. And then we know that it'll be 180 minus the pink angle will equal x. Okay, so if I look for that angle, it looks like it's just below the fish's mouth. Okay, so if I look over here in the shape they gave us, there's the fish's mouth. The angle just below it is 150. So this would still be 150 in this fish. So if I do 180 minus 150, that leaves 30 degrees left for x. So x would be 30 degrees. So again, let's take a look at that again. So what we did is we just transferred this angle. We just transferred this angle from this fish to that same corresponding angle in that next fish. We knew that those were both 150 degrees because it's the same size fish in both places. And so then if that has to make a straight line there, that left 30 degrees for x. Okay, and that's all we've got for today.